Okay, let's dive into something truly foundational today. It's a concept that's really changing how we build digital stuff. We're moving away from, the explicit step-by-step instructions we're used to
Right.
towards code that actually, well, learns from data.
Yeah.
And understanding this shift, it feels increasingly important for anyone thinking about digital tools and their impact.
Absolutely. It's a really fundamental change in thinking, not just a new feature or tool. Our main source for this discussion is a really insightful essay called Software 2.0.
By Andrej Karpathy, yeah.
Ah,
It lays things out with remarkable clarity.
it really does.
So our mission today is to unpack this Software 2.0. What is it really? Where is it already showing up? What are the upsides, the downsides? We'll be pulling insights straight from that text,
Exactly. It's about getting a handle on this because the essay argues it's not just niche tech. It's fundamentally altering how digital systems get made.
which is, crucial as these systems become more and more embedded in everything.
Yep.
So maybe the best place to start is with what came before. The essay calls it Software 1.0. What are we talking about there?
Right. Software 1.0. That's basically the software development we've known for decades, the classical stack, as the essay puts it.
So code written by humans.
Yeah, exactly. Humans sitting down, writing code line by line in languages like Python or C++, Java, what have you.
You're giving the computer explicit instructions. Step 1, do this. Step 2, do that. If this happens, do that instead.
Precisely. You define the behavior directly. The essay uses a good analogy. You write the source code, say a .cpp file, and then a compiler turns that into a runnable program, a binary, human instructions, packaged up.
Okay, so that's 1.0. Now, Software 2.0. The essay presents this as something fundamentally different, right? Not just an upgrade.
Fundamentally different. It's a different paradigm. The
Okay.
code itself isn't written in those languages. It's more abstract.
Abstract how?
Often, it's represented by the weights, the numbers, inside a neural network. And we're talking millions, sometimes billions of these numbers.
Right, and the key point the essay makes is that no human is writing those millions of numbers directly. It's just too complex.
Way too complex. You couldn't possibly specify them all manually.
Okay, so if people aren't writing the code line by line, how does Software 2.0 get created?
Instead of writing instructions, you specify a goal.
The goal, like what?
Like get really good at identifying cats in photos or win this complex board game. You state the objective, then you provide a sort of skeleton, the basic structure that's the neural network architecture.
Okay.
And then you use a lot of computation, that's the training process, to essentially search for the right set of weights, the right numbers for that network that actually achieves the goal you set.
So it finds the program that works.
It finds the program. Yeah, the trained network is the program.
Let's go back to that analogy from the essay. For Software 1.0, the source code was the .cpp file. What's the source code for Software 2.0?
According to the essay, the source code is really the data set you provide. That data set basically defines the desired behavior. That plus the network architecture you choose.
And the compiler. What turns that source into the final program?
The training process itself is the compiler. It takes the data and the architecture and compiles them into the final binary, which is the trained neural network with all its specific weights set.
Wow, that's a really different way of thinking about building software. And it implies a shift in what developers actually do, doesn't it? The essay talks about this.
It really does. Most of the effort in the Software 2.0 world isn't writing lines of code anymore. It's about the data.
Finding it, cleaning it, labeling it.
Exactly. Curating data sets, growing them, making sure they're clean and well labeled. That's the work of the 2.0 programmer. You still need traditional 1.0 programmers, but maybe more for building the tools and infrastructure around the data and training.
Okay, so why is this shift happening? Why move from explicit instructions to this data-driven learning approach? The source gives a pretty clear reason.
Yeah, the core driver, it argues, is that for many, many real-world problems, especially messy ones involving images or sound or language, it's just way easier to gather data showing what you want.
Than it is to sit down and write explicit rules to cover every single possibility.
Exactly. Trying to code rules for, say, recognizing any object in any lighting condition, that's incredibly hard with Software 1.0, but collecting millions of labeled images, that's feasible, though still a lot of work.
And the essay makes that pretty bold claim, doesn't it? Something like, Software 1.0 is eating the world, and now AI, Software 2.0, is eating software.
Yeah, it's a strong statement. It suggests this isn't just an alternative. For certain domains, it's becoming the dominant way.
So where are we actually seeing this happen? The essay gives quite a few concrete
Oh
examples.
yeah, lots of them. Visual recognition is a big one.
How so?
It used to be about engineers clever designing features like edge detectors or specific shape templates for the computer to look for.
Mhm.
Now,
Now it's neural nets.
almost entirely, yeah. Especially convolutional neural networks or convnets. The essay points out it's become a search problem, searching for the best network architectures, trained on huge data sets like ImageNet. They're even using AI to help design the AI architectures now.
That's pretty meta. What about speech recognition? Understanding spoken language.
Huge transformation there too. We moved away from these complex multi-stage pipelines with, acoustic models, pronunciation dictionaries, language models often involving things like GMMs and HMMs.
Lots of engineered components.
Lots of engineered components, lots of linguistic assumptions. Now, it's largely end-to-end neural networks that learn directly from raw audio to text. That's where that famous old quote attributed to Fred Jelinek back in the 80s comes in.
The what about firing linguists?
Yeah, every time I fire a linguist, the performance of our speech recognition system goes up. A bit provocative, maybe, but it highlights how data-driven learning started outperforming handcrafted rules.
Okay, making computers talk. Speech synthesis.
Same story. Went from somewhat robotic-sounding systems that stitch together little bits of recorded speech.
Right, you can sometimes hear the joins.
Exactly. To modern systems, like WaveNet mentioned in the essay, often using large convnets that generate the raw audio waveform directly. Much more natural sounding.
Machine translation, too. That feels like it changed almost overnight.
It really did. Older statistical methods like phrase-based translation were largely replaced by neural machine translation models. And the essay notes some cool developments, like single models handling many languages, or even learning to translate with less direct supervision.
It even mentions things like games and databases. That seems less obvious.
Yeah, games are maybe more intuitive now. Think AlphaGo beating the world champion Go player. That wasn't explicitly programmed with Go strategies. It learned through self-play, a Software 2.0 approach. A conjugate was at its core. The essay predicts similar takeovers in games like Duoda 2 or StarCraft.
But databases, how does Software 2.0 fit there?
The essay points to research on learned index structures. The idea is to replace core components, like B-trees, which are highly optimized Software 1.0 data structures used for indexing.
Right, fundamental to databases.
Replace them with a neural network trained on the specific data in that database. And the research showed that in some cases, these learned indexes could actually be faster and use less memory than the traditional B-trees.
Wow. Okay, that could have some serious implications for efficiency, especially with, say, large government datasets or something.
Potentially, yes, though it's still an active research area. The author does note, importantly, that many of these examples were coming out of places like Google at the time, who were really pushing this frontier.
Makes sense. And there was that mention of one model to rule them all.
Yeah, a hint towards a possible future where maybe you don't have separate models for images, text, sound, but perhaps one massive Software 2.0 system that understands across modalities.
Yeah.
A long way off, maybe, but it's part of the vision.
Okay, so we see it happening across the board. What are the big advantages? Why make this switch? Apart from just, it works better. The essay lists quite a few benefits.
Right, works better is the easy answer, but there are deeper architectural reasons too. One is being computationally homogeneous.
Meaning?
Unlike a complex C++ program with tons of different instructions, a neural net is mostly just doing tons of simple math. Matrix multiplies and simple activation functions, like ReLU.
Okay.
Because the building blocks are so simple and uniform, it's easier to make hardware that's really good at doing just those things very fast and efficiently. And it's easier to reason about performance.
Which leads to the next point, right? Baking it into silicon.
Exactly. Because the operations are simple, you can design specialized chips, ASICs, neuromorphic chips, optimized purely for running neural nets. This means you can get AI into smaller devices using less power. Think smart sensors, on-device voice commands.
That enables intelligence to be more pervasive.
That's the idea, low-power intelligence everywhere.
The essay also mentioned constant running time and memory use. How's that a benefit?
Well, unlike some complex Software 1.0 code where, depending on the input, it might go down different paths, loops, maybe even get stuck, A standard forward pass through a neural net takes a predictable amount of time.
Okay. More predictable.
Yeah, and same for memory. It typically uses a fixed amount during inference, less chance of those tricky memory leaks or unexpected resource usage you can get with complex dynamic allocation in 1.0 systems. For building reliable systems, that's a big plus.
Portability was another one?
Right. A sequence of matrix multiplies is pretty standard.
Hmm.
It's easier to run that same computation consistently on different hardware, from a phone chip to a cloud server, compared to a complex binary compiled for a specific environment.
And then there's this idea of agility. The essay even calls it magic. What's that about?
It's about how easy it can be to tweak and improve. In Software 1.0, making a big system significantly faster often means a major, complex rewrite.
Right. A huge effort.
With Software 2.0, if you need it faster, you might just make the network a bit smaller, fewer parameters, and retrain it. Performance might drop slightly, but it's often a straightforward trade-off. Need it to be better.
More data. More compute.
Exactly. Get more data, or use a bigger network and more computing power for training, and often the performance just improves. That cycle of improvement can be incredibly fast compared to traditional development.
And this idea that modules can meld.
Yeah, this is really interesting. In 1.0, you connect components through fixed interfaces, APIs. In 2.0, if you connect two neural net modules, you can often train them together end to end. Information flows back through the whole thing during training.
So they kind of tune themselves to work together.
Precisely. The essay gives examples like a browser optimizing low-level instructions or a vision system tuning itself for your specific data. It allows for a kind of cross-component optimization that's hard in 1.0.
And then the final, maybe most direct benefit listed, it is better than you.
Yeah, a bit blunt, but the point is, for certain tasks, especially perception tasks with images, video, sound, speech, a well-trained neural network can often simply outperform human-written code in terms of accuracy or robustness.
Okay, so lots of compelling benefits.
Yeah.
But it can't be all sunshine and roses. What are the downsides, the limitations mentioned in the source?
The biggest one, and it's a really significant one, is the black box problem.
Hard to understand why it does what it does.
Extremely hard. You might have a model that's 99% accurate, but you have almost no insight into its internal reasoning. Compare that to a maybe less accurate, say 90% Software 1.0 system where you can trace the logic step by step.
And that lack of understanding, that opacity can be a real issue, especially, in areas needing transparency or accountability.
Absolutely critical issue. If a system denies someone a service or makes a recommendation, you need to be able to explain why. And with many Software 2.0 systems, that's incredibly difficult right now.
This can also lead to weird failures.
Yes. They can fail in ways that make no sense to a human. And sometimes, as the essay points out, they fail silently.
Silently.
Meaning they might seem to work fine, but they've picked up subtle biases from the training data. Maybe it performs worse for certain demographic groups, for instance. Detecting and fixing that bias in a massive, opaque network is a huge challenge.
Which is, again, really important if these are used for public-facing applications.
Crucial. Fairness and equity require very careful attention to the data and ongoing validation.
The essay also mentions peculiar properties, like adversarial examples.
Right. The fact that you can change just a few pixels in an image imperceptibly to a human and cause a top-tier network to completely misclassify it, it just highlights that these systems don't see or understand the world the way we do. They can be brittle in surprising ways.
So putting together this Software 2.0 approach code written by optimization based on evaluating performance, where does it fit best?
The essay argues it's best suited for situations where you can't easily write down the rules yourself.
Like recognizing a cat.
Like recognizing a cat or understanding nuanced language. But, and this is key, you need to be able to repeatedly and cheaply evaluate how well the program is doing.
So you need a clear metric, like classification accuracy or winning the game or translation quality score.
Exactly. If you can measure success easily and often, then optimization can search for a program that maximizes that success.
And thinking of it as a whole new programming paradigm, not just another tool in the toolbox, seems important for understanding what comes next.
It really is, because it reframes the whole development process and highlights what's missing. We need a whole new ecosystem to support this way of building software.
New tools.
Totally new tools. We have amazing IDEs, debuggers, version control, like Git for Software 1.0. What does the equivalent look like for Software 2.0?
An IDE for data.
Pretty much. Tools to help manage these massive data sets, visualize them, clean them, label them efficiently. The essay suggests things like tools that flag potentially mislabeled examples based on what the current model finds confusing.
Oh, interesting.
Or tool that actively help you label faster by providing suggestions, or identifying which new data points would be most useful to label next to improve the model the most. Data curation becomes the core programming task.
And version control for data sets, a kind of GitHub for data.
Yeah, imagine that, where a commit isn't a code change, but maybe adding new labeled data or fixing labels or documenting a cleaning step. How do teams collaborate on building and refining these crucial data sets?
And then actually sharing and deploying the finished product, the trained model.
Right. We need standardized ways to package, share, and deploy these software 2.0 binaries. The essay mentions something like a conda for neural networks, easy ways to manage and distribute these trained models so others can use or build upon them.
So what's the short-term outlook here, according to the essay?
It predicts software 2.0 will just keep expanding into areas where evaluation is cheap and writing the rules is hard. And there's a huge amount of work and opportunity in building out that ecosystem, the tools, the workflows, to properly support it.
And the really long-term view, the essay gets quite ambitious there.
It does. It states pretty directly that the author believes artificial general intelligence, AGI, if and when it arrives, will certainly be written in software 2.0.
Wow. Okay. So, wrapping up, this shift is clearly fundamental. It's changing how we build the systems all around us. Understanding this move from explicit instructions to learned behavior feels, well, essential.
It really does, and framing it as this distinct paradigm, software 2.0, helps clarify both its immense potential and, the significant challenges and work still ahead, especially around tooling and understanding.
It leaves us with a pretty deep thought, doesn't it? If the source is right, and the future of advanced AI is likely software 2.0, intelligence built not by explicit human design, but by optimization learning from data, what does that really imply about the nature of that intelligence? Or even about what programming itself will mean down the line, especially when we think about building systems we need to trust? Lots to chew on there.